We talked about this before, but when we look at an organic molecule, for which we see three examples right here, functional groups are clusters of molecules that give molecules their chemical properties. And so we discussed that the carbon and the amount of carbon defines the size of the atom, of the molecule, which matters quite a bit. But the fancy things that it can do, or the dramatic things that a molecule ends up doing, are determined by these atom clusters that we call functional groups. They define the molecule's functions. And here's an example of a functional group. We can see on both aspirin and ibuprofen that we have this carboxylic acid that's hanging off of the molecules, that COOH group that we've seen before. And this kind of makes sense, right? That aspirin and ibuprofen therapeutically have similar roles. As such, there are some similarities in the functional groups that are present. Other functional groups are like this ester group, where we have this COO, but not a hydrogen on one side. It bridges between carbons. And so we'll look at a table of what these are, but for now, just note that these similar bonding themes are appearing on multiple molecules. Here's another example, this H2N. So this is a nitrogen at the end of a molecule. And we saw previously that when there were a lot of these nitrogen-hydrogen groups, that this ended up making a molecule highly polar. We saw that with metformin in the previous video. That's another functional group. And while this benzene ring isn't exactly a functional group, it's a really characteristic carbon ring. This is a ring of 6 carbons that are alternately double bonded. This comes up an awful lot as well, and while it isn't technically a functional group, it does lead to similarities because it's just got a distinctive size and chemical behavior. Okay, some common functional groups are as follows. So here, going from the top to bottom, we start with a hydroxyl group, OH, or an alcohol group. If we just have an OH that's got carbon stuff on the other side, we call this an alcohol, and an example here is ethanol, which is shown here in the top of this, right? This is CH3CH2OH, and that's our example of ethanol. A carbonyl group is a carbon double bonded to an oxygen, and this one actually appears in both this one and the next group, but when we have this carbonyl group, it ends up being chemically somewhat active, and it does give some general properties that are similar as well. So when we see a carbon double bonded to an oxygen, we call that a carbonyl. It will have some reactivity associated with it. But a special class of these carbonyls is this carboxyl or carboxylic acid, which is that COOH that we've seen previously. And that's here shown with acetic acid. This is vinegar, and we've actually investigated this molecule quite a bit already. Another class of the carbonyl containing elements, or carbonyl containing molecules or functional groups, is an ester. We saw this previously. This is that COO group that has carbon stuff on either side as well. This is the third one on the left, and here we have an example of an ester containing molecule, ethyl acetate. And finally, a couple of nitrogen containing ones. We have an amino group. Here's methylamine, which is just nitrogen bonded to a carbon, and then those are both saturated with their hydrogens. And finally, an amide. An amide is really distinctive for peptide bond formation and is shown here. This peptide bond is this really characteristic link between a carbon and a nitrogen that makes up how proteins form, and we'll investigate that further. So here are some common functional groups. I'll include these on the exam sheet. The big point of functional groups is that these functional groups determine the big parts of how a molecule will react, the physical properties it'll have, what it's going to dissolve in, and things like that. And so here are some examples for each of these, where they're found, as well as the properties for each of these groups. Generally speaking, right, when we look at a molecule, if it's a really, really large molecule and it has one hydroxyl group, that's not going to be as determined by the hydroxyl group's behavior as if it's a really, really tiny molecule with one hydroxyl group. Or if it's a really large molecule with 5 hydroxyl groups, that'll behave differently than a really large molecule with 1 hydroxyl group. So the amount of these groups that are present on a molecule totally matter as well. We want to look at different molecules and say, wow, this one is really defined by the presence of these types of groups that's what leads to getting an understanding of chemistry based on the functional group. But remember as well that to look at a molecule and say, oh, I look at that and I know exactly what that molecule does with no other experience, that's really not feasible for anybody. And knowing what a molecule does and most likely does, or sort of the behaviors that it is likely to have, that's a reasonable starting point, even if beyond the scope of this course. And for the scope of this course, the idea is just that there are common repeating functional groups that we're going to see on molecules, and that these end up giving those molecules potentially similar classes of behavior.